Good afternoon and good morning. Welcome to the peer-to-peer webinar. My name is Zhenli here, a third-year PhD student from the University of Tokyo. I'm gonna present the impacts of ethylenediamine, that's a crystallization and morphology of calcium carbonate during wet-carbonation. This presentation will give these 5 parts. In this graph, it shows approaches to carbon neutrality in the cement and concrete industry until 2050. In order to achieve carbon neutrality, we should consider the concrete in service, concrete production, cement and clinker production. Well, on the top of this, we also need a technology carbon capture utilization and storage, the CCUS. What we can find in this graph is that the percentage taken by carbon capture utilization and storage is high, is almost more than 1/3 till the middle of this century. Here, there is meaning to carbonation technology. Indirect carbonation and direct carbonation. Direct carbonation is more applied in the construction industry. It carbonates cementitious materials with carbon dioxide under dry, semi-dry, and wet conditions. The dry means no humidity or water involved in the whole carbonation process. The semi-dry means the water keeps the pore solution partially saturated. The wet means to direct carbonated material with carbon oxide in the water solution. Due to the high efficiency, low energy consumption, and great adaptability of wet carbonation, will focus on the wet carbonation only. The next step is how do we control and utilize the carbonation products. The nature is able to grow very strong and durable calcium carbonate with different kinds of structures and performance features, and it is really achieved by some small organic molecular proteins or the bioenvironment. Inspired by this, the biochemistry industry has already applied some organic molecules to control the polymorph of calcium carbonate to form different types of calcium carbonate like calcite, vaterite, arugite, and amorphous phase. If we do the same thing in the wet carbonation, we can better apply the more dissolvable vaterite and amorphous phase to better serve in the recycled concrete or personal care biomedical production. So the objective of this study is to investigate the effect of ethylenediamine on the calcium carbonate morphology control. The ethylenediamine is widely used in the biochemical field. We shortly called it as EDA. And what we try to do is to selectively precipitate these 3 types of calcium carbonate and understand how does this process goes. We prepared 3 types of materials: the hardened cement paste, calcium hydroxide, and calcium carbonate. We put these powders into the DI water with the CO2 bubbling in. At the same time, we add 0.15% of EDA. And after carbonated from 0 to 4 hours, we filtrate the solution to get the precipitates and the supernatant and to analyze them with its techniques. The first is about the EDA structure change with carbonation. We do this by the carbon 13. The x-axis is the chemical shift, and the y-axis is the intensity of these peaks. The chemical shift comes mainly from these 2 regions, 38, 48, 160, and 170. These three types of peaks comes from the carbon at different position of the EDA structure from EDA2 plus or EDA carbonate. And the peak here is from EDA from the carbonate itself, and the peak here is from the carbonate or bicarbonate. We conclude the structure change of EDA with carbonation here in this table. At the first moment till 4 minutes, the EDA has transformed to EDA carbonate, while in the later age, the carbonate exists with the EDA1 plus or EDA2 plus. Next, we use total organic carbon to detect the carbon in EDA. The TOC, the total organic carbon TOC represents the concentration of EDA in its organic structures, while the carbon in the carbonate or bicarbonate is inorganic carbon. This is a result. The y-axis represents the EDA concentration in the liquid phase. We prepared three types of systems: calcite, cement paste, and portlandite. We found the absorption starts after 4 minutes of carbonation, and in the cement paste system, more than half of the EDA is absorbed in the solid phase. While in the polymorph, the absorption is even higher. We also confirmed that the EDA doesn't absorb on the calcite itself. It means it must go into some carbonated phase in the cement paste or the portlandite. The next, we check the EDA reaction with calcium ions. We add different concentration of EDA into a saturated polymorph solution, and we found the concentration of the calcium go higher with the EDA concentration, which means the EDA promotes the dissolution of polymorph. This is from the complexation reaction. So we go to the real wet-carbonation of the cement paste. This is a pH change with different addition of EDA. The red line is a normal wet carbonation without any EDA addition. It proceeds in 3 stages due to the different stage of carbonation of hydrates from their different dissolubility. The pH drop here has been shifted by EDA to an early drop and a long-lasting drop through the whole carbonation process, which means the dissolution and the precipitation among these hydrates, the balance is broken. Besides, the EDA does not affect the initial and the final pH. This is a calcium concentration change in the liquid. The red dot is normal carbonation. Calcium decrease with carbonation, and the later increase because the CSH decomposition release calcium. The aluminum phase first dissolve cause the increase here, and then the precipitation of aluminum gel cause a decrease here. When we add 1% of ethylenediamine, the orange line, the trend is not changed, only the volume is changed. But if we add a higher amount of EDA, we found not only the volume goes to like 10 times higher than the normal wet carbonation, also the trend is go the opposite way. This indicates that the precipitation order in a normal wet carbonation, that from calcium carbonate first and then aluminum or silicate gel second, now is altered by the EDA addition as high percentage. The silicon is mostly from the dissolution of CSH. It decreases when the EDA added, meaning that the CSH dissolution is slowed down. This is about the characterization of the solid phase. This is a mass change of portlandite and the carbonation degree in the whole system. On the left figure, the portlandite amount is not changed so much by the different additions. Though the carbonation degree, especially the carbonation speed in the several 16 minutes, is greatly slowed down by the EDA. The final carbonation degree is increased, especially at 10% of addition, which means the CO2 fixation efficiency is improved by the EDA addition. This is a calcium carbonate mass change detected by XRD adding no 1%, 5%, and 10% of ethylenediamine. We also carbonates the pure portlandite with 5% of ethylenediamine. In the normal carbonation system, the bar denotes the amount of calcite, iridium, and vaterite, and the blue line is the amount detected by TG. And here we found these two values are always consistent. So if we add ethylenediamine, we found there's always a gap occurs. We attribute the gap between the value detected by these two techniques is from the amorphous phase, because TG can detect all the calcium carbonates, where XRD can only detect the crystal phase. We also confirmed by the FTIR that the material here is indeed from the amorphous calcium carbonate. So therefore, from this comparison, we found when ethylenediamine is added, a large amount of ACC phase is formed, and it will transform to calcite at 1% of addition. But if the dosage is high, the ACC will transform to vaterite finally. I also confirmed the formation of ACC and vaterite in the 5% of addition by SEM, that it is from the 16 minutes after carbonation and 4 hours after carbonation. Next thing is about discussion part. Here firstly, we wonder what role does EDA plays during wet carbonation. It has 3 effects. First, it complexes with calcium ions. This is confirmed already by ICP before. And second is the EDA promotes the absorption of CO2. In the early age, the amino group can react with carbon dioxide to form carbonates. And in the later age, it maintains a high pH in the system. The CO2 can react with CO2 dissolution is promoted by the hydroxide ions in the solution. And the third is its absorption with amorphous phase. The upper lines is the EDA concentration in the solution detected by TOC, as we shown before. And the lower lines is the amorphous calcium carbonate amount detected by XRD and TG differences from the calcite, paste, and portlandite. In the portlandite system, there's only portlandite and calcium carbonate phase. So the absorption here comes from either the portlandite or some forms of calcium carbonate. The portlandite here will disappear from 30 minutes and later, but the desorption still go on, which means the absorption happens among some types of the calcium carbonate. The calcite here, we have confirmed the absorption is not from calcite, so it must from the vaterite or the amorphous phase. Here, the decrease of the absorption and the increase of the amorphous phase go very parallel. So therefore, we conclude the third effect is from the absorption between EDA and amorphous phase. Then next, we discuss how the amorphous phase is formed and crystallized. This is a classical crystallization theory. And first, the ACC is formed. The ACC cluster is formed in calcium-containing solutions, and the ACC dissolves and grow into the vaterite spherulite. And the second step, the spherulite or the ACC will keep growing throughout Ostwald's ripening. And the third step, the larger size vaterite will grow and transform into calcite due to a dissolution and the reprecipitation process. This is how this phase will change with time. The green line is ACC, and this is a vaterite, and this is a calcite. On the right figure, this is an enthalpy of different phase in the calcium carbonate. And the ACC is the most unstable phase, with the calcite is the most stable phase. By this theory, it is mentioned that the calcium supersaturation is very important. It is the prerequisite of the ACC formation. Because when the supersaturation degree is low, the crystallization and the crystal growth is slow to form the well-ordered crystals. The met and stable calcite will be precipitated. Well, if the saturation degree is too high, the nucleation and growth is so fast and so accumulated in the solution to form the well-ordered crystal structure. Thus, the metastable vaterite or ACC will precipitate. This is a saturation index of ACC calculated in our case. The higher the saturation index, the higher potential dissipate of ACC to be precipitated. In the case of no ethylenediamine, the saturation index is low. That's why we only get a calcite from the classical carbonation. If we add EDA inside 1%, the saturation index get higher, so we get some precipitation of the amorphous phase. And if we add more EDA inside, the more ACC phase we will get from 30 minutes and later. There's no polymorph existing in the system, so the calcium saturation index is decreased. So the ACC from here will transform to vaterite. We conclude here the complexation between the EDA and calcium highly increases the saturation index in the solution to precipitate the metastable ACC or vaterite phase. This schematics will show how EDA changes the crystallization process of calcium carbonate. In normal wet-carbonation process, it grows from calcium ions to ACC clusters, vaterite spherulite, and larger size vaterite, and finally transform to calcite. Where the EDA is added, more calcium will be dissolved because of the complexation process, and they were kept by the EDA to maintain a balance between the ACC and the vaterite spherulite. Therefore, there's no crystal precipitation from the solution. And later, when all the potlandite is consumed, the calcium supplement becomes very slow. So the calcium concentration becomes so low that the ACC will unidirectionally transform grows to the vaterite spherulite, and the spherulite will grow and finally transform to calcite at 1% addition and to vaterite at 5 or 10% of addition. This is the conclusion of my presentation, and thanks for your listening.